Greetings, everyone. All right, so here's an infinite series example from an old AP exam. We Some of us are still struggling with some of the pieces of figuring out how to answer these infinite series questions on the AP. So I thought I'd go over an example for you. And here's the question. It comes from the 2011 Form B. They don't make Form B test anymore the way they used to, but Form B was for those people who missed the test for a legitimate reason on the first time around. I don't know how they handle it now, but nonetheless. So, 2011. Let f of x be equal to the natural log of the quantity 1 plus x cubed. And then for part A, the Maclaurin series for the natural log of 1 plus x is equal to this series here. And it says use the series to write the first four non-zero terms and the general term in the Maclaurin series for f. So notice the nice thing about this example or this problem here is that they give us the series that we're going to be manipulating. They're not asking us to derive the series for the natural log of 1 plus x, which they certainly could have. They're giving it to us and seeing if we can manipulate it to answer the questions that they need. Also notice that they want the general term to be given. Sometimes they ask for the general term, sometimes they don't. And so we have to just be aware when they do that we be sure to give it to them. So we'll come back and read the other ones when necessary. So here, I've already pre-written the natural log of the quantity 1 plus x. And so to generate the series for the natural log of the quantity 1 plus x cubed, all we're doing is we're replacing x with x cubed. And so all we need to do is just that. Okay, so the x that I have here becomes x cubed. The next x again becomes x cubed squared over 2, and then we're going to have x cubed, and that's going to be over 3 minus x cubed to the fourth over 4, and then plus dot dot dot. I'm already taking up too much space here, but nonetheless plus, and then just keep the form the same, negative 1 to the n plus 1, x to the third power to the n over n plus dot dot dot. Now you don't need to simplify this. You can leave it just like that, provided you write clearly. I'm going to change this bad looking 3 here. That looks better. You don't need to simplify this to get the credit for this question. You can just leave it like this and go on to the next question. So don't necessarily simplify it, although the next question is going to require us to be careful because we should simplify to answer the next question. But we can stop there for this one and be done with it. And by the way, this is a 2-point question on that exam. The first four non-zero terms were worth 1 point, and then they gave 1 point for the general term. All right, let's go back and take a look at part B. Part B says the radius of convergence of the Maclaurin series for f is 1. Determine the interval of convergence. Show the work that leads to your answer. So, we could show using the ratio test what the radius of convergence is, but again, that's something they're giving to us in this example, and they want us to try to work out the interval of convergence. So, they're saving us a lot of work that we've done in class in many of examples, but in this example here, we don't have to do that. So, if we know the radius of convergence, let's go ahead and approach answering this. If we know the radius of convergence, what we need to do now is think about what the center is for the series, and then once we know the center and the radius, we can figure out the majority of the points in the interval of convergence, and then we have just a little more work to do after that. So let's think this through. Since this is a Maclaurin series, okay, we know the center is 0, and since the radius of convergence is 1, the interval of convergence is at least the open interval from negative 1 to 1. So we move from the center 1 unit to the left to negative 1, and then one unit to the right to positive 1. And so now all we have to do is to test the endpoints. And actually, what I mentioned a moment ago about needing to simplify what we just did in part A is not till a later part of the question. It wasn't part B. But nonetheless. Alright, so we know, as I was mentioning, we have the open interval negative 1, 1. We may include the endpoint. So let's see. If x equals, let's say, positive 1, then what does our series look like? Okay, well, let's go back and take a look at it. Well, if I plug in positive 1, I'm going to get 1 minus 1/2 plus 1/3 minus 1/4 and so forth. And so we're going to get the alternating harmonic series. And we just write that down. This is the alternating harmonic series which converges. Well, that looks terrible. Which converges. And then we go through the analysis if x equals -1. Now, if x equals -1, so take a look at our series over here. Then I get -1, and well, then the next term is going to be negative also, if you look at it. Even when I square the cube, that term is going to become positive, but I'm subtracting it, so it's going to be negative. And then the next one, I'm going to have x to the 9th. When I simplify that, putting in -1 makes it still negative. Then the next one will be negative, and they're all going to be negative. So this is actually the opposite of the harmonic series. So we're going to get this series here. Work it out by hand. Take the time for a moment for yourself if you don't see what I'm saying, if I'm doing it a little too quickly. But you should be able to see that. Okay. So, and we know that this, and you state what it is. This is the opposite of the harmonic series, which is divergent. And now that we know that, and then we can state the answer. So the interval of convergence, and my writing's a little sloppy here, I apologize. Convergence is, I don't even remember now. When I plugged in 1, it converged, and when I plugged in -1, it diverged. So the half open, half closed interval -1, 1. And this was also a 2-point question. I don't remember how they allocated the points, but it's a 2-point question. All right, let's go look at part C. Now for part C, write the first 4 non-zero terms for the Maclaurin series for f prime of t squared. And then if g of x is the definite integral from 0 to x of f prime of t squared with respect to t, use the first 2 non-zero terms of the Maclaurin series for g to approximate g of 1. Alright, so we need to break down the function that we're asked about first right here into 2 different steps. Okay, so we need f prime of x, and then we need f prime of t squared, and that's how you want to break this down and think about it. So first, we have our function f, which is, this one we already generated the series for, f of x equals the natural log of that quantity 1 plus x cubed. So we're going to take the derivative of that, or rather its infinite series, term by term, and then we will substitute in t squared, term by term, to get the Maclaurin series for f prime of t squared. And then for g of x, we're going to go and we'll integrate term by term and work this part out over here. We'll get to that in a moment. So several things that we need to do. All right, let's get to the page. I went back and I simplified f of x. And if when we plugged in x cubed, we're raising x cubed to the next integral power. So raised to the second power, we get x to the 6th, then x to the 3rd cubed is x to the 9th, then x to the 3rd to the 4th is x to the 12th, and then x to the 3rd to the nth power is x to the 3n. So that's that. So as I mentioned a moment ago, we want to find the derivative. So f prime of x is going to be 3x squared minus 3x to the 5th power. I'm already simplifying, when I bring the 6 down as a multiplier, 6 divided by 2 is 3, so I'm already working that part out. And then we're going to have plus, and then we're going to have, looks like we're going to have 3x to the 8th. And then we're going to have minus 3x to the 11th, plus plus negative 1 to the n plus first power. And then when I bring down the 3n, the n in the 3n will cancel, or the n in the 3n will cancel with the n in the denominator. We'll be left with 3 times x to the 3n minus 1 plus dot dot dot. So that's what the series should look like up to this point. Now I did do a little too much here because it only asked for the first 4 non-zero terms, and I gave the general term too. There's nothing wrong with that. Just be careful though. You don't need to do more work than is requested, because if you make a mistake, they could still mark something wrong. So now we want the first 4 non-zero terms for f prime of t squared, and so f prime of t squared, I should be able to squeeze this down here if I leave the general term off, will be 3 t squared squared, t to the 4th, and then minus 3 t squared to the 5th, t to the 10th, and then plus 3 t squared to the 8th, or t to the 16th, minus 3 t squared to the 11th, which is t to the 22nd power. Sorry, lost my train of thought there. And so there's that part. Now let's think about this last, well, there's still 2 more parts of the questions we have to do, I guess. But let's think about generating the series for g of x. And so we're taking the definite integral from 0 to x of this f prime of t squared with respect to t. And in doing this, we're using the fundamental theorem and, our theorems connecting calculus and the infinite series, the stuff that we learn in AB. We're going to integrate term by term our series, but then by the fundamental theorem we'd have to plug in x and then plug in 0 and then subtract. But every term we have is going to be a term in terms of x. So when I plug in 0, the terms are going to disappear. So what we're going to end up with is just our antiderivative term by term with x's instead of t's. It's all you need to do to answer this question here is to go ahead and integrate, find the antiderivative term by term, and then plug in x in place of all the t's, and then I don't even need to have a constant of integration because this was a definite integral. And so for g of x, getting a new screen here. Alright, the first term, we're going to reverse the power rule, so add 1 to the 4, divide by that, we'll get 3/5 t to the x to the 5th. Again, we're switching over to x because we're kind of combining steps here. Is if we did this in terms of t first and then plugged in the x, it's extra work that we don't want to necessarily take the time to do. And then minus, and then we're going to have 3/11 x to the 11th. And then we're going to have plus 3/17 t to the 17th. And then lastly, minus 3 over 23 t to the 23rd power. Whoops. Plus dot dot dot. And then the last part of the question was to use the first 2 non-zero terms of g to evaluate g of 1. And so the first 2 non-zero terms for g of 1, so g of 1 is approximately equal to, if I plug in 1 for x, I get 3/5 minus 3/11. You could stop right there because remember, on the AP exam, you don't have to simplify expressions. You can leave it just like that. That's correct. If you want to find a common denominator and simplify it, it's okay to do so, provided you don't make any mistakes. But why bother to take the time and risk the mistake? So I'm not even going to do anything with it. I'm going to leave it just like that. Okay. So that answers that part of the question. All right. So let's go all the way back. Whoops, and take a look at part D. It says the Maclaurin series for G evaluated at x equals 1 is a convergent alternating series with individual terms that decrease in absolute value to 0. So in that sentence right there, they're giving you a lot of information to save you a lot of work. They don't want to see you do this work. They want to see what you can do as a result of this work. So, excuse me, they're telling us that it's alternating. we saw that, okay? They're telling us that, or we could see that, but they're telling us that. They're also telling us that the terms, individual terms, decrease in absolute value to zero. So with those things in absolute value to zero, with that, excuse me for stumbling there, but what that's telling us is that by the alternating series test, that this alternating series will converge. They're letting us know that from the start. So this is, now for the question, show that your approximation in part C must differ from g of 1 by less than 1/5. Alright, so your approximation must differ from g of 1 by less than 1/5. What does that mean? Well, g of 1 is the actual value. My approximation is just that. It's an approximation. So if you're thinking clearly about this, the difference between g of 1 and our approximation has to be the error of the series that we're just talking about. So this is asking us to show that the error in our approximation is less than 1/5. Okay? So that the error in our approximation is less than 1/5. Realistically, we're looking at the magnitude, okay? Must differ. The way they worded this, we're looking at the magnitude of the error, okay? So what I'm trying to show is, let me get all the way to the last screen here, that this value here differs from g of 1 by less than 1/5. So I want to show that the error has a magnitude, I'm going to put that in before I forget it, less than 1/5. Well, how would I calculate the error for a alternating series? Well, for an alternating series, the error in magnitude is less than or equal to, so I should not have an equal to sign here, is less than or equal to the first term we left off of the series. Well, if we were adding the series together here, the next term would be this term that we have up here, this 3/17 t to the 17th, but evaluated at 1, so it gets 3/17. So the error in our approximation has to be bounded by 3/17, the first term that we left off. That's what our alternating series estimation theorem tells us. So our magnitude of our error by the alternating series estimation theorem is bounded by 3/17. But 3/17 is less than 1/5. Now you really just should state that. You really don't have much to show here. The comparison of the two fractions, if you want, you could rewrite 1/5 as 3/15, and then that kind of shows that you thought about it a little bit. But I don't even think they require that. I think that once you just find the correct error bound by the alternating series estimation theorem, and you should be able to recognize that 3/17 is smaller than 1/5, because 1/5 is 3/15. If you break something up into 17 parts and take 3 of them, or break something else of the same original size into 15 parts and take 3 of them, 3 of the 15ths is going to be a bit bigger than 3 of the 17ths. So the error is less than 3/17. And that's really the end of the problem. Now this is just a 1-point question, believe it or not. Part D was worth only 1 point. I didn't mention Part C, how many points it was. It was a big one, 4 points. We had a point for finding f prime. We had a point for finding f prime of t squared. We had a point for finding g of x, and a point for finding g of 1. So that was the most heavily allocation. That had the most heavy allocation of points to it. So I hope that was helpful. Think about how the question was asked, and think about how we went through the analysis and what types of things they were looking for, and what types of things we need to concentrate on showing based on how the question was worded. Go study.